Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you so much, Anna. Good morning, afternoon, and good evening, everyone. Thank you for joining this session. I would like to thank Professor Young for also making time to give us this session titled From Semantic Communication to Semantic-Aware Networking. So in this talk, Professor Young is going to talk about classic semantic communications frameworks and also summarize the key challenges that hinder its popularity. In this talk, we are going to observe that semantic communication processing or processes such as semantic detection, knowledge modeling, and coordination can be resource consuming and also inefficient. So the argument is that the semantic aware networking will also have potential to fulfill the vision of intelligence of everything for the next generation communication systems. So I would like now at this moment to welcome Professor Young, who is a professor of the School of Electrical Information and Communications at the Hangzhou University of Science and Technology in Wuhan, China. Welcome, Professor, to our webinar, and good afternoon.
Hi, good afternoon.
So I would like to thank you for coming and give you the floor for this interesting session. Thank you.
Okay. Thank you for having me. So let me share the screen. Okay, now you can saw the screen, right?
Yes.
Okay, perfect. Okay, and thank you everyone. This is Yong Xiao from Huazhong University of Science Technology, and I'm also with Pengcheng National Laboratory. And this work is a joint work with Guangmin Shi from Xidian University and also with Pengcheng National Laboratory. Okay, these are the basic outline of this talk. So first, I will give a brief introductions about why semantic communication is important for future, especially the AI native networking. And also then I will mainly focus on introducing three of our work that is trying to addressing some of the issues involved in the semantic communication as well as semantic aware networking. And finally, I will talk about some open problems. Okay, let's get started. And so first of all, as you all know, that the wireless technology has evolved tremendously during the past few decades. And traditional wireless systems are mainly built on the data-driven based solutions, focusing on just a single goal, that is maximizing the number of data bits communicated per second. With the recent global rollout of 5G, the wireless technology has started to transform to the service-driven solutions, with a whole new service-based architecture has been adopted in 5G, targeting at three different service scenarios, like including the eMBB, focusing on further improvement of the data communication speed, and then URLLC, targeting at ultra low latency and high reliability scenario, as well as the massive machine type communication, MMTC, that is trying to maximizing the connectivity density of the network. So the next generation of wireless systems, the so-called 6G, expected to continuously evolve to a more intelligent and human need-driven paradigm, enabling a plethora of innovative smart service, such as holographic type information, tactile internet, as described in the ITU-T Network 2030 series of specifications, with the eventual goal to bring human-like intelligence into almost every aspect of the network. Despite of the paradigm change during the past few iterations of wireless evolution, however, the fundamental theory and solutions has been largely unchanged. So in particular, the Shannon's information theory has been serving as the fundamental for almost all existing communication engineering systems. In his seminal work, published in 1948, Shannon defined the fundamental problem of communication as that of reproducing at one point either exactly or approximately a message selected at another point. Despite of the huge success of the Shannon theory in the modern communication systems, researchers have started to think about some other possibilities to further improve the communication efficiency. In fact, the Shannon theory has been coined by Weaver in 1949 as a just level one communication problem, and also being referred to as a technical problem of communication, because Weaver believed it just focused on accurately transmitting a content irrelevant symbols. Weaver believed that a more general theoretical communication theory should also involve two other levels of communication problem, including the so-called semantic problem, focusing on how precisely do the transmitted symbol convey the desired meaning, and also the effectiveness problem, focusing on how effectively does the received message affect the conduct of the source user in a desired way. In fact, Shannon has intentionally ignored the semantic when he developing his information theoretical framework. As described in his 1948 paper, Shannon claimed that semantic aspects of communication should be considered as irrelevant to the engineering problem because it may affect the generality of the theory. In other words, semantics are hard to present, extract, and compute, and can be affected by many personally related aspects such as the language, background, personality. To summarize, from the communication engineering perspective, unlike binary bits, semantic meaning is not a universal sense to be involved in the communication. Although semantics are hard to understand by machine and computer, the human brain has worked brilliantly in recognizing, memorizing, communicating, and learning based on semantics. Recent study in neuroscience suggests that the capability of human brain to manipulate semantics is closely related to the so-called semantic systems. That is, a neural systems widely distributed in more than 100 different regions of cortex in both sides of brain hemisphere. Different regions of cerebral cortex in the semantic systems can be activated in various patterns when recognizing different semantic meanings. In contrast to the previous conclusion that semantics are highly personal, recent experiments suggest that actually the activation patterns observed in the semantic systems across different individuals with different background and personality are actually surprisingly consistent. Here we show a recent published paper published in Science, and that is describe an experiment conducted by a scientist from UC Berkeley. They have studied the whole brain blood oxygen level dependent, also called the bold responses image, recorded by fMRI of 7 different individuals when listening to the same set of stories. It then adopts a voxel-wise modeling approach to build up a prediction model to estimate the possible activation patterns that is across different regions in the semantic systems when listening to different words associated with different semantic features or semantic domains. So after comparing the predicted model with the recorded brain activity, the result shows that the prediction model works very well. And actually the semantic systems of different individuals exhibit very similar patterns when listening to the words with the same semantic meaning. Some other results also suggest that a similar pattern can also be observed when words with the same meaning are listened or observed by human users using different ways, right? So this means that there might exist a universal mechanisms for the human beings to generate and infer semantic meanings. Okay, so another question is that how human beings can store and assess the existing, the already learned semantic concepts in the semantic systems. So previous studies has believed that human brain encode and store concepts individually like a dictionary. However, how different concepts are connected and also how the semantic relations are affecting the semantic system of human brain are only investigated very recently. A recent study conducted recently by the faculty from University of Michigan observed that the human brain uses distributed network to encode not only concepts, but also relationship between the concepts. They observed that the cortical pattern encoded of the relation, for example, here we show the whole part relation in the slides. It's actually the figure from that paper, is that the relation is actually independent of the cortical representation of individual words in the relation, right? So this means that the connecting different words with different relations will significantly change the semantic meaning it expressed, at least from the activation, and also activate different parts of the human brain. In fact, the relation between words can be the key to the semantic meaning. Another experiment conducted by a researcher from Aalto University, also published recently in the 2020, demonstrated that how humans are able to recognize objects and understand their rich meanings by reasoning based on relations, even when only limited information about them is available. So in their experiment, participants receive clues of an individual objects in the form of 3 isolated semantic features. For example, here on the slides, we show 3 different figures, 3 different clues given with a target object elephant, as shown in the paper. So it turned out that the recorded brain activity patterns of these participants shows that not only the 3 semantic features given as the clues, but a far richer set of semantic features linked to the target objects have been activated in human brain's semantic systems. For example, not only the gray, hertz, and tusks of the element has been activated in human brain, the human brain will also show the activation patterns of a lot of features surrounded by the elephant, like the big animal leg, etc. So in other words, the human brain is able to infer the complete semantic representation of objects from only the fragmented information, while there are potential relations between them. This also verifies the very original definition of semantics made by French linguistic Borel in 1897, that the semantics are in fact the relations between vocabulary and the knowledge they represent. Also, it also shows that semantic can be computed and inferred based on the relations with various attributes and feature set. So to summarize, the human acquires semantic knowledge by building up relations between different concepts and as well as their attributes. The human brain will be able to automatically link fragmented information together and obtained through perception to a very specific objects by inferring their relations with all the other relevant features stored in their brain. In other words, compared to the traditional communication solutions, the semantic communication focus on recognizing the semantic meanings by combining the received signal with the knowledge learned from the past experience. The main objective is not to accurately restore the original form of symbols, but to make the destination user possible to infer intended meaning of the source user. In other words, the information loss is tolerable in the semantic communication as long as the lost information is relevant to the key meaning of the source user. This makes semantic communication heavily depend on probabilistic computing and fuzzy logic to achieve meaningful inference and interpretation at destination users. The main research interest of our group focused on developing novel reasoning-based mechanisms and architecture to enable semantic learning, cognition, and communication, as well as reasoning throughout the next generation of communication networking systems. So in the rest of the talk, I will basically discuss some of our recent efforts towards this goal. So our vision is to make the next generation of networking systems to have the human-like intelligence to understand and reason about the real need of the human users and support innovative new application service to meet those needs. To achieve this goal, we have been actively participating in standardization efforts in the ITUT, as well as IMT 2030 6G promotion group in China. So in the rest of this talk, I'll briefly introduce 3 of our work related to reasoning-based semantic communications. Our first work is about reasoning-based implicit semantic communication. So this work is motivated by the fact that in addition to the explicit semantics, because a lot of existing work in the semantic communication, they focus on just communicating the explicit information, such as the label of objects that can directly identify it from the signal source, for example, an image or voice. However, the content of communication information may also consist of rich implicit semantic information that can be very critical for understanding and efficient delivery of the real meaning of the user. It is known that a different user can have different interpretations of semantic meaning when observing the same signal. So in the example shown in the slides, we can show the text message with a we can show a text message with an explicit semantics. For example, the word apple can be directly identified from the source message. However, the word apple can actually either refer to a fruit or a smartphone brand. None of this information can be directly recognized or inferred from the text message itself. So the true meaning of the word apple means will need to be inferred from the context, as well as the previous communication history or some of the background of the users. In fact, the implicit causality among concepts and ideas in the communication message can be utilized to further reduce the redundancy of transmitted signal, and as well as recovering some missing or corrupted information at destination user. And most importantly, they can help to discover new unknown information concepts that can support novel self-learning and self-evolving solutions for some highly advanced autonomous decision-making process, hopefully in the future networking systems. Despite of the huge potential, implicit semantic communication are very difficult to establish. So because generally speaking, the implicit semantic meaning are very difficult to present, recognize, and interpret. As a matter of fact, the implicit meaning often involve many complex hidden relations and entities that are very difficult to present in a simple and comprehensive way. And also, the implicit meaning can be very closely related to user-related information, and it's very difficult to estimate and infer. Finally, accurately recovering and evaluating the implicit meaning at the destination user is also very challenging, because most existing work assume there are already an existing like reward function or well-formulated decoding scheme that can directly output the intended message based on the input signal. However, in implicit semantic communication, the destination user must jointly consider a wide variety of information, and therefore including both the signal received from the channel as well as the background, personality, and previous communication history to make sure the semantic information can be successfully interpreted. So in this work, we adapt a graphical inspired representation of semantic information consisting of entities involving both visible and hidden entities. And so, for example, in the previous example, the apple can be considered as a visible entity because it has been showing on the content in the text. While some other entities like fruit or smartphone, a brand are hidden entities. And also the relations also include visible and hidden relations. For example, in a text message, Tweety is a cartoon character. The visible relation is, and there is also hidden relations. If the inference result is given by the Tweety is a cartoon character in a TV show, right? Then the later part in a TV show is the implicit information that we need to infer. The core of implicit semantics is the reasoning mechanism. And that is a mechanism that can output the possible relations and hidden entities based on the given set of visible entities and relations. Here we present our possible implicit semantic communication architecture, which consists of a source user and destination user, a physical channel, and also a knowledge base for both users, including both commonly shared knowledge as well as the private knowledge. So in the source user side, it consists of three key components. The first one is called entity detector. the encoder should first identify some of the visible entities as the initial clue, right? And then a semantic encoder will try to convert the semantic representation, the high dimensional graphical representation, into a low dimensional semantic space. And finally, a semantic comparator will be deployed to compare the previously observed expert reasoning results with the results reasoned or inferred by the destination users. So the destination user side will consist of a very key component in the implicit semantic communication architecture. That is the semantic interpreter, which has a main function to output the implicit semantic meaning based on the received entity sent from the source signal and corrupted by the physical channel. In particular, once received the corrected semantic representation sent from the source, the decoder or the semantic interpreter will try to recover the most probable reasoning relations and entities that link to the observed entities. So as mentioned earlier, the main objective of semantic communication is to minimize the meaning difference or minimize the meaning dissimilarity between the original meaning as a source user and that interpreted by the destination users. An intuitive approach to implement the above semantic encoding solution is to design a simple projection function known by both source and destination user to separate the different entity in the that associated with, for example, different semantic domains or class according to their meaning difference, right? So in other words, the entity associated with the same class or same semantic domain should be very close to each other in the semantic constellation or semantic space, compared to those associated with different class, right? The different class of semantic entity should be further apart in terms of their Euclidean distance. So a graphical representation of the semantic meaning of the 7 concepts associated with 2 classes connected by 8 relations is shown in the bottom side of this the slides. So as well as their corresponding semantic constellation is shown on the right-hand side. So let's now introduce the proposed optimization algorithm. So how can we train the model? How can we train the projection functions, right? So, so the basic idea is that we develop a joint optimization solution referred to as the generative imitation learning based solutions that can jointly train the semantic comparator and semantic interpreter. So the semantic interpreter can learn a reasoning mechanism with the help of comparator at the source to automatically infer some hidden entities and relations based on any given visible entities sent from the source. In particular, the semantic comparator can observe a set of expert reasoning paths from a previous communication. So during the training phase, the destination user will periodically feedback some reasoning results that they made based on a very limited number of clues to the source user. And the semantic comparator at the source will train a neural network to differentiate semantic meaning between the expert reasoning results as well as the reasoning results submitted by the destination users. So in other words, the comparator will try to just train a neural network with the following loss function shown at the bottom of this figure of the slides. And for the semantic interpreter at the destination user, we follow a commonly adapted setting and assume this relational reasoning process based on any given set of entity with a given knowledge base can be formulated as a Markov decision process, in which the main objective is to train a policy that can specify the probability distribution of choosing the possible hidden relations to further extend the reasoning path from any given set of visible entities. So our proposed MDP-based solutions consist of the following component: the state. So the state means that each reasoning state is sequentially generated by choosing the hidden relations one at a time. And the action is that given any state, the action space will provide a set of all the possible hidden relations extended from the current state. And also we have a reward function that is associated with the most possible reasoning solutions. The most probable solutions, the higher the value obtained by the reward. And finally, the most importantly is the policy. The policy is is basically can be considered as a mechanism that maps the current state into the probability distribution of the finally reasoning results with all the possible combination of hidden relations and hidden entities. So the main objective of the semantic interpreter is to train a neural network to minimize the cross entropy between the expert reasoning meaning results observed by the source user and that the generated meaning interpreted by the destination users. Okay, so we conduct experimental results based on New 995, a popular knowledge-based dataset. We generate some subgraph to simulate the semantic meaning that made by the source user. So in the figure on the left-hand side, we compare our proposed the generative reasoning mechanical learning algorithm with another reasoning solutions called a generic algorithm. So these another algorithm, the GA, is a popular heuristic knowledge inference solution based on population evolution and competition. So we can observe that our proposed generative reasoning mechanical learning solution offers at least 20% of performance improvement over the GA in all the three considered subgraphs. So on the figure listed at the right-hand side of the slides, we consider the lossy channel transmission of the semantic message and evaluate the semantic communication. And we evaluate the semantic communication performance by our proposed generative solutions by investigating the symbol error rate. So these are the semantic symbol error rate of the semantic communication in an additive Gaussian noise channel. As mentioned earlier, the accuracy of semantic reasoning is closely related to the knowledge structure of the considered subgraph. For example, the density of the connections among the connections, the closer the meaning among those entities, the higher the density of the relations connecting between different entities. So the easier for a different entity to infer the possible existence or infer their possible relationship with each other. So in other words, to investigate the impact of meaning similarity of different like error correction performance, we consider 10 different subgraphs ranked from 1 to 10, from the lowest diversity to the highest one. And in other words, the semantic diversity of here we show SKG1 has the lowest diversity, and the 10 has the highest diversity. So we can observe that compared to the traditional communication solutions without any reasoning solution, our generative reasoning mechanism learning solution can provide 18 dB improvement under, for example, the SNR equals to 4 dB. So in terms of semantic symbol error rate, we can also observe that our proposed solution can significantly improve the robustness of communication, especially when the diversity of the message and semantic diversity of the message is limited. Okay, in the figure, in this slides, on the right-hand side, we present a semantic constellation of the subgraph generated using our proposed projection function with some entity associated 3 different classes sampled from FB15K, another knowledge database. We can observe that the 3 different classes are separated in different semantic aspects when being represented at different, for example, dimension corresponding to the image and real part of the constellation. And also on the right-hand side of the figure, we show that the reasoning and prediction accuracy, the past reasoning accuracy under different dimension, because originally speaking, if the number of dimension is too small, will easily cause underfit. While if the dimension keep increasing to a very large dimensionality, then will easily cause the overfit. So that explains our figure shown on the right. And we present 3 subgraphs sampled from 3 different knowledge graphs, the WN18, New 995, and FB15K. And we show that the optimal dimensional size for our sampled dimension of the semantic constellation space are given by like 24, 46, and 62 respectively. So this observation once again verifies the communication efficiency of our proposed solutions, because we are transmitting just a semantic constellation instead of all the attributes and required knowledge of the graph. Our second work is focused on a lifelong learning process for reasoning-based semantic communication systems. So this work is motivated by the fact that to make the future network to be more sustainable and also have the capability to learn by itself or self-evolve, it needs to overcome some of the obstacles that are very challenging for the existing networking systems. For example, in the existing communication network or network AI, the recognizable semantics are always limited by a predefined closed set. And also the transmitter, in fact, sometimes the transmitter may use some new concepts that is unknown to the receivers or the rest of the participant of the communication. Therefore, there is a problem on how to continuously learn new knowledge and automatically update the reasoning model during the communication, right? So here we show examples that, for example, if the original user understands the apple is a fruit. However, when a new concept comes over by saying that Apple is also a brand that is a smartphone brand started by Steve Jobs. Then this new knowledge must be included into the representations, right? So how to continuously learn a new knowledge and they automatically update the semantic interpretation model at the receiver is still an open problem, right? So in this work, we are focusing on minimizing the long-term semantic distance, including that is the meaning dissimilarities between the transmitted message of the source user and the meaning interpreted by the receiver during a long time frame, right? Because we allow them to have sequentially learn from the past. So we follow the same implicit semantic communication architecture, and therefore, in this case, the key is to design a more general projection function that is easy to update and also can very quickly capturing the key difference in terms of the meaning between concepts in a structurally different semantic knowledge base, especially in terms of diversity of knowledge concepts and also the terms within the knowledge base. So here we designed a very general inference function to differentiate the positive and negative combination of positive means most possible. That is basically already shown in the past, as well as the negative one, it means that less unlikely in the past communication content. So in other words, the inference function should be able to map the plausibility of any given pair of entity and relation to a single value. The receiver will then be able to use the mapped value to decide whether this entity and relations are likely to be combined when interpreting the meaning of the user. To map the possible combination of the entity and relation into a single value, we introduce 3 possible functional bases in our projection function to characterize the additive, linear, and multiplicative relationship between different entities and relations in the semantic space. So the 3 projection functional bases as shown at the bottom of the slides. So let's now briefly describe this knowledge updating procedure of our proposed lifelong learning scheme. So at the beginning of the communication process, the transmitter and receiver cannot observe all the knowledge entities and relations. But they can obtain a certain communication history and also sequentially learn and update an inference function F to convert the graphical representation of semantic meaning into a low dimensional semantic space, like the semantic constellation we've shown in our previous slides. In particular, at the beginning of the training process, the transmitter will try to use the previously observed successfully combination of entity and relation as the positive training samples. And he can also randomly generate some unobserved combination as the negative samples. That means that those combinations should never happen, right? Both positive and negative training samples will be sent to the receiver to train an initial model that try to separate the positive one and negative one. The transmitter and receiver will then observe during the communication, when the new combination of entity and relation are observed. This new combination of entity and relation will be added to the positive training samples. And if these newly appeared combinations of entity and relations are also in the previously generated negative training samples, then they should be removed to the positive training samples. In this case, the training sample set will be updated and the training process will be repeated. Since the inference function will only be updated when a new unknown knowledge being appeared, right? So for example, new entity, new unknown relations, or an unknown combinations. So in other words, as more and more message can be communicated and learned between the source and destination, then the chances of discovering new unknown entity and relation will decrease significantly. And our results show that it's actually decreased exponentially, right? So the chances, in other words, when the chances of discovering a new knowledge and in new unknown terms decreases into very minimum level, means that we have already successfully trained a very popular model that's fit for most of the scenarios, right? So here are our simulation results. We use, once again, a knowledge-based data set, WN18. We generate some random subgraph to mimic a semantic message. And in the figure on the left-hand side of the slides, we evaluate the impact of different forms of inference functions on the convergence rate of the model training. And we present the value of loss when the two inference function, and that is additive inference function functional basis and linear inference functional basis under different iterations. So we can observe that during the first few rounds of training iterations, the linear inference function offers a faster convergence rate. However, when the iteration goes large, then the additive function will have become to surpass, will have a much faster convergence speed than the linear function. So compared to the linear function, the additive function is relatively easier to compute and offer a better convergence performance, which makes it an ideal inference function for example, in our simulation results, we show it's actually a very good one for the WordNet-based data set. And that is, however, might not be the case, because we also have some other results showing that in some other data sets with very complex relations between entities, the linear function may exhibit a faster convergence rate than the additive one. So next, we evaluate the accuracy of the semantic meaning of the interpretation when the model is trained with different number of training samples. And in the figure shown on the right, we evaluate this meaning recovery performance based on the reasoning and inference. So in this case, the receiver can use the reasoning rules established based on our projection functions to infer the missing semantic information. Our solution achieves around 76 and 48% of accuracy in recovering the missing information when using additive and linear inference function, respectively. Okay, so in the first two works, we are focusing on semantic communication between a single source and a single destination. So they have to train and iteratively updating with each other for a continuously learning and updating their local knowledge base as well as the projection function to improve the communication efficiency. And then our final work we would like to discuss is focused on the semantic-aware networking, right? So we can observe that some semantic communication process, such as semantic detection and knowledge modeling and coordination, can be very resource consuming and efficient, especially for communication between a single source and destination, right? So because a single source and destination will try to train a model, but if the model only used for communication between the single pair, then it's highly efficient in terms of the training efforts, right? We therefore propose a novel architecture for supporting the knowledge and model sharing in a semantic-aware networks. Our architecture is motivated by the fact that the knowledge is generally very hard to share, and maintaining a unique knowledge base for each user requires huge communication and storage overhead. And also the training of model and accumulation of knowledge take a lot of time and may require tremendous computing resource. Also for the semantic-aware networks, the model collaboration and privacy security issue also contradict with each other because the communication parties or participants need to exchange knowledge constantly to learn from each other, which actually increase the risk of privacy disclosure. So our proposed architecture consists of a set of users that can be either source or destination users, a knowledge base including both commonly shared knowledge as well as the private knowledge that is only accessible for some individual users. And these knowledge base, as well as the semantic encoder and decoder decoding models are all stored and maintained by edge servers that deployed just very across the entire network. And we assume each edge server is deployed closer to an exclusive set of users. So, and then we adopt a federated edge intelligence-based architecture in which multiple edge server can coordinate to train and update the same machine learning model without exposing their local knowledge data or data samples. There is also a coordinator that is focusing on coordinating the model training and learning among different edge servers. This can be deployed at one of the edge servers or on the cloud. Right? So the key model training procedures is described as follows. So in our architecture, all the above components will interact by performing the following procedures. Right. So first of all, each user, either source or destination, will sense the surrounding environment to obtain a partial observation or reception signals about the communication environment and scenarios. So each source user will update its sensing result together with the source signal. Will just upload the sensor results to the edge server for semantic encoding or decoding. The edge server will always search for the suitable models to detect the meaning of the signal and then generate the required message, encoded message, sent back to the source user or destination user. So instead of directly detecting entities and the relation from the signal, the encoder and decoder should also have the capability to learn and reason about possible form of relationship and implications. So in the case that some of the knowledge terms in the signal uploaded from some of the user cannot be perfectly recognized, for example, is unknown or new, then in this case, edge server will extract some features based on the context of the communication of these unknown elements, and then evaluate the relationship of this new term with the existing elements, as well as the existing knowledge relations. And then they can update the models, semantic encoding and decoding model accordingly. So let's now present the simulation results. In the figure on the left, we evaluate the consumption of 3 types of resource, like the running time, local storage, and the required number of training data samples for training a simple CNN models in our network. We use the cross entropy as the loss function, and the training process terminates when the target accuracy level is on the, like here we present a different runtime, right? As shown on the figure, could be a 98%, 98.8%, or 98.9%, etc. So our result shows that even running on a very high performance GPU server, the time duration for training the AI model could reach like up to over 300 seconds. So passing the time duration for directly transmitting a high resolution image file or most of the files on the wireless channels, right? Using existing technology, for example, 4G, 5G, and Wi-Fi. And we can also compare, the resource requirement of different individual server when 2 or more edge server can collaborate and help each other in training a shared model with a target accuracy level. Our results show that both the required storage and number of training samples per edge server decrease with the number of model sharing edge servers. And therefore the total runtime reduced to less than 1/4 of the time with 8 collaborative edge servers. So this verifies the effectiveness of our proposed federated edge intelligence architecture in terms of reducing the source consumption for each individual edge server. So on the right-hand side, we also compare the rate of GCN-based solutions using 3 citation network data set, including the CiteSeer, PubMed, and Quora. And as we can see that if the reasoning-based solutions can be applied, then the compression rate can be significantly improved, especially in our figure shown on the right. We show that the compression rate is actually closely related to the knowledge structure as well as the correlation of the data set. In particular, for the Quora and CiteSeer, actually it could be only significantly reduced compared to the Quora, compared to the PubMed. right? So we also present the distortion rate, right? When the destination user does not have any knowledge base, but need to receive more relation-based information from the source user to minimize the distance, right? So so between the signal at the source and that recovered by the destination users. So from this figure, we can observe that the semantic communication is able to achieve much lower like error probability or symbol error rate, because the reasoning and inference can be applied, so they can recover some of the lost information through the context. Okay, finally, let's talk about some open problems. So there are actually a lot of open problems towards semantic communication, as well as the semantic-aware networks. So the first one is the knowledge evolution tracking, because we all know that human knowledge is actually evolve over time, because they are not stationary. So how to model and keep track of temporal variations? For example, how to aggregate new unknown entities at very accurately and also very efficiently, and also how to discuss some obsolete information to save space or reduce the reasoning time of each individual knowledge base are actually very helpful, right? So these are very important to provide a sustainable network solutions with continuously improved communication efficiency, as well as reduce the probability of error, because the human knowledge, when they evolved, there could be some error, misunderstanding of some concepts when the concepts has new meanings, right? So so far, there's still a lack of a very efficient way to develop the how to track of the human evolution, knowledge evolution, and also coordinated with the network systems. Another one is secure model sharing and transferring. So our proposed semantic-aware networking architecture allow each pair of source and destination users to jointly train a private model. Some private model that can identify new knowledge elements available only at some local areas. So if we transmitting those models into some global models or some other parties, they could result in some of the privacy leakage or some other issues. So therefore, in this case, we do need some other efficient and private preserving solutions that can support, continuously support the model sharing and transferring. And another issue is how to quantify the network layer quality of experience. It is known that the different people with different age, genders, personality, and cultural background may have different focus on their personal experience under different conditions, right? So how to develop a novel compositional experience matrix that can covering essential experience indexes for diverse type of people interested in problem is an actually very interesting problem worth further investigating. And finally is the capacity. What are the capacity of semantic-aware networks, right? As we mentioned earlier, that the capacity of semantic network can be significantly improved by applying the reasoning or some of the other inference, like by deploying the human-like intelligence into the network. However, what are the limits, right? So because when involving the intelligence or computational into the network system, the capacity problem will become much more complex. It could be also related to the knowledge base, inference model, and knowledge sharing schemes of different users, right? So developing an elegant and comprehensive mathematical framework to evaluate the performance limit is an important direction for the study. Okay, and that's all for my talk. And here's my contact information, and all the paper and slides can be downloaded on my webpage. And thank you for your time. And now I'm open to take questions. Thank you.
Thank you so much, Young, for the time and presenting this quite interesting talk. I would like to go to the Q&A session. So welcome, Vishnu, and good afternoon.
Thanks, Thomas. Thank you, Young, for that excellent talk. There are a couple of very interesting points that you raised. Jose is asking the question that I was thinking about. What are you standardizing? So you mentioned about your efforts in standardization in ITU and others. What exactly needs to be standardized? Is it relationships? Is it semantic space that you talked about? or is it the encoding mechanism that you talked about? What are you trying to standardize here, and could you talk a little bit more about that?
Okay, thank you the question for the Vish. So actually, we try to currently involve some of the project in the ITUT. There are several ways we want to further apply the semantic awareness into the network in the current standardization framework. Because although our framework is actually, we try to put some breakthrough on the 6G. However, we do believe the semantic awareness can actually enhance the existing, like IMT 2020 network architecture, by deploying some of the, for example, mutual interface of the model, reasoning model or learning model, at least with some interface. Of course, we don't try to, for example, standardize specific reasoning approach because that is still developing. But still, how can we apply a certain number of interface into the network to make the network can evolve with a human or understand some of the meaning of the user, instead of always, when you're, for example, have some errors of information, you're always asking the transmitter to resend, right? In other words, sometimes you can reasoning or understand some of the very useful informations. Another issue is that, for example, there are some misinformations or some privacy issues we do believe can actually be sequentially adapted, applied into the existing network architecture. That's our current efforts.
Thank you so much. I think that your in your architecture there are several things which can be looked at standardization, especially your approach to measure and your approach to validate. That itself may be quite interesting. Personally, I think it would be interesting to see different entities used a standardized mechanism for measuring and evaluating the performance of semantic communications itself. But let us go to the next question. Expert input. Yeah. So in your architecture, you did talk about knowledge base. You did talk about expert input. I had the same question. Miltiades is asking the same question that I had. What is the role of this knowledge base, and what is the size of this knowledge base? How, in your experiments, in your benchmarking that you showed in your simulations, did you use any specific knowledge base? Could you talk a little bit more about this role of this knowledge base, and especially what he is asking, what happens when the knowledge base is missing altogether, or we don't have that relationship information with you? Could you talk a little bit more?
And thank you very much for the questions. Actually, about the semantic, the knowledge base, is that actually we try to consider the knowledge base is a accumulation process that human, when they interact with each other, the base will start graduating. We try to let the network to more mimic the human behavior, because the human, like a kid, right? They have zero knowledge, and then they start graduating and establish a relation, learning the connection between different concepts, different knowledge. And this knowledge base can, at the moment, we actually try to consider as the two type of knowledge base, right? The first one is common one, that is common sense. That is basically should be known by everyone. There is no privacy at all, because everyone should know this facts. So even if you know this knowledge base, it doesn't matter. So some of this kind of knowledge base can be applied into networking to recover some of the very basic common sense error, or some very, or depending on the scenarios, right? If we consider some smart factory scenarios, that factory can have some particular local knowledge base that can specify most of the commonly scenarios could happen, right? So in other words, when there's some damage or attacks or abnormal things happens, it will be directly recognized instead of just alarm the people, right? They can directly know what is nonsense, what are the nonsense happens, or what are the unreasonable things happens. Another thing is that we try to have some private knowledge base that can only be stored in your mobile phone or in your personal device. That is for example, you're communicating with your buddies, with your friends, close friends. The more closer you with your friend, then they should communicate less, because that's how a human works, right? Because if you're talking to your very close friend, they are very less likely he will misunderstood you. So we hope the network can have the self-learning capability that the network, when they coexist with human, the longer, the better they understand the human needs. So that's the two part of the semantic knowledge base that we try to propose in this architecture.
Very interesting. Very interesting. Thank you so much. There are a couple of more questions which are here. Could you talk a little bit about, I think in slide 4, you did talk about high level, what the use cases are. You mentioned some very high level use cases in slide 4, I think.
Slide 4?
In general, yeah, in slide 4, yeah. I think it was very, very beginning. So what are the use cases that you see for this kind of semantic communications? You list here, there are some here which you are talking about, but specifically, what are the use cases? All right, right. Alev is asking exactly the same question. So what are the use cases? Could you talk a little bit more about specific use cases that you have in mind?
Actually, that's actually very closely related to one of our standardization efforts at the SG20 on the IoT and smart city and smart community study group. So we have a technical report being initiated last year that talking about how can we apply semantic communications or semantic-aware networks in a large IoT or smart city scenarios that we can, for example, pre-store some of the like knowledge, or pre-store some of the commonly knowledge that is shared in the smart community. So when the people talking about something related to relevant to the community or some of the IoT service they want, they can automatically get a response, and also the network will understand the human needs, and then they can start to learn gradually when they offering the smart service. Like a smart city, when there are, for example, in the past, there's some failure, and then they can start to learn from the past and gradually improve a certain knowledge base, and eventually make the network to be more understand the human meaning. So that's a first issue that we do believe the IoT smart city and smart community will be a big issue. And another one is, we hope, is a smart factory, because the factory also need to understand some of the, for example, the efficiency of the worker or management, right? So we try to make this network more human-like, because they can, for example, if the new human user want to get hand of some new machine or new factory, instead of reading the manual or learning from the zero, from the zero knowledge, they should be able to interact with the network and understand more, and also the network should also cope with different users' needs, and also like the workers' needs or management needs. So that's our consideration. And we are actually currently we try to do some of the small experiments on the visual conference systems that we are currently developing a software to demonstrate some of the potential of the semantic when in the future the online conference does not have to be the real person, it's digital person, right? So we try to detect the human frame and the key point of your face. Then we can detect your expression, your emotion, and then we can generate some funny face or something to be applied into some online conference for some entertainment. That's our current efforts.
Interesting, very interesting. Thank you so much. The data sets that you were using, you had several data sets that you referred to. Are these open? Can we take a look at it offline, or are these private data sets that you are referring to? Could you what are the characteristics of these data sets? Are they computer vision, images, videos, or is it text, natural language? Could you talk a little bit about your data sets?
Okay, so our data set is come from several, it's not image data set, they all knowledge knowledge data set. For example, the WordNet is like a dictionary. So it type all the words with the relations connection with them. We also use some citation data set. So they all, for example, social network, Wikipedia data set, we also use it because that is link different knowledge with different relations. The citation network will link different papers. For example, the similar topic paper will be linked to each other, while the paper belongs to a different area will be considered as one type, same semantic domain. So that's the data set we have been using. And the reason we're using that is that because we try to mimic the scenario that people, when you talk, the content of your talk should come from a very small piece of that knowledge set. And then, which means that all the message should be meaningful message, right? Instead of just random image, we don't know what exactly. So we try to using some subgraphs randomly sampled from the big knowledge data set, and then we take out some of the relation to assume these relations are hidden or you don't know, and then we try to train our reasoning mechanisms, and so they can directly recognize what are the hidden relation and what are the hidden entities. So that's how it works.
Thank you so much. And are these open data sets or are they private?
They all open data set.
Thank you. Thank you. Next, Piotr is asking, in work 3, in the third part of your work, I guess you talked about continuous new knowledge, learning new knowledge and updating the reasoning model. I guess that's what he's talking about. How do you recognize, how do you detect that something is new? That's an interesting question. So first, to update, you need to understand, you need to detect that there is something new. How do you detect this delta knowledge, as Piotr calls it?
Thank you. It's a very good questions. So in some scenarios, there are some new terms appears in, for example, some sentence. That terms could be you never understand, or there's a new terms showing on the internet that is seem to be that does not exist in your existing knowledge base. So in that case, we will try to build up a link, the link based on the context of that word. For example, the previous word or subjects of that word contains some other existing relations. And that's how we build up an initial one. And then because this is an unknown relation or entity. If the unknown entity relation, for example, if an image, let's consider image, then it means that there's no way we can recognize because the accuracy of recognizing that objects is very low. If in a context, then it's a text message, then it's very easy to understand, oh, this is a word that does not exist in the semantic base. In that case, we try to link with the some other objects or relation coexist in the same, for example, same text message or the same image. Then in that case, we try to searching for the relation of this existing existing known knowledge existing in the text message. And then we try to, of course, in the beginning, we can only, if we have very, very limited knowledge about this new term, we can only randomly generate some random relation with the existing context. But when we saw receiving more and more this different context with also involving this unknown message, will keep improving the accuracy of this network. And eventually we will build up, because the key that we only focus on building up the relation between this new term and the existing knowledge term. So that's how we're sequentially doing it, by receiving more and more context information.
Thank you so much. In the existing communication mechanisms, there is a lot of importance for the channel. We try to predict the channel, we try to estimate the channel, we get feedback about the channel. A lot of importance is there for the nature of the channel. Can you compare it that scenario with what your research is saying about semantic communications? What is the role played by channel estimation, inferring the channel, basically understanding the channel?
Okay, thank you for the questions. So this is a very good questions. The thing is that, as you can see here, we show some of the one of the examples of the semantic constellation we are building up. These are the constellation can be considered the symbol to be transmitted on from the source. So first thing is that we try to build up this constellation by allowing some, for example, the close meaning, some different term with very close meaning to be very close to each other. So when noise, for example, Gaussian noise be adding up, then there's most likely that even there's a misinterpretation, but still the most likely term will be, for example, even there's a misunderstanding, but the concept has been changed to another concept, but the concept will have very close to meaning compared to others. So that's one difference between our proposed semantic constellation and the previous one. The second one is that these are the frameworks that we try to jointly train. The channel model has already been involved into our training process, because the transmitter will send, for example, in this page, in this slides, the transmitter will send for example, a certain already compressed signals into the channel, and the channel receives this corrupted signal. In other words, for the destination user, it can only reasoning based on the corrupted signal, because the destination user never observe the original signal observed by the source. In other words, they also do the training, so they have to generate a reasoning results and feedback the results to the source. So the source will always, the whole model will train already with the channel condition built up into their model. In other words, finally, the destination user will be fit perfectly, very good when they interpreting the source, the signals, the meanings, because the source already, because the channel condition has already been involved into the training process.
Very good. Thank you so much. Then I guess we are kind of coming to the end. I want to ask you about optimization and fitting this model into the UE. What is your take on that? So the inferred model or the semantic comparator and encoder, this has to, how do we optimize it and fit into user equipment, which may not be so resource powerful. So what kind of optimizations are you looking at? Are you looking at such problems of optimizing these models, please?
Yeah, currently we try to optimize the model in several ways. For example, in this particular model we propose in our first work, like implicit semantic communication, the key point is that the source will not always try to send, because the thing is that the semantic interpretation or the meaning interpretation has to be done by either source or destinations, right? So in our architecture, we prefer let the destination to understand, let the destination to interpret. So the source don't have to transmit a lot of information. So in other words, the source, the main objective of the source is try to, for example, help assist the destination to understand what they mean. They are not try to, for example, maximize the number of information sent to the channels. So these are the way we are currently working on some sequentially model to improve the thing. Another thing is that we try to consider a network scenario, because as we just mentioned in our last work, that if you learn so hard by consuming a lot of resource by training just one particular model that fits only for one source and one user, that's definitely highly inefficient. So we hope the whole network can have, that's the reason we hope this certain standardization efforts can be built up. The network can start collecting a certain type of information, or at least know some information that we can build up so we have more useful model or informations when we build up 6G standardization efforts or 6G network architecture, right? So the network setting will definitely be more efficient. So that's actually our main focus on the network scenarios.
Very interesting. So that means that you need to know what goes on in the network so that you get more and more context, and also looks like your optimizations at the receiver end. Are more interesting, especially in case of downlink. Very interesting talk. Thank you so much. Thank you for patiently answering all the questions. Over to you, Thomas.
You're very
Thank you so
welcome.
much, Vishnu, for moderating the Q&A session. And I would like to give a big appreciation to Professor Young for making time to make this presentation and have this discussion. Quite interesting what kind of work is going on for future communications. Very much interested in this semantic communications. So I would like to give a big appreciation to you. Thank you for making time.
Thank you for having me.
And at this time, I would like also to thank everyone who joined today's session. Thank you so much. Thank you so much for joining the session. And I would like also to inform you that we have more sessions in the coming weeks. Also, please note that there are several AI for Good sessions. You can check on the program. If you go to the AI for Good webpage, you go to the program, you find several events that may be of interest to you. At this point of time, I would like to close and we'll see you in the networking session. So please stay by in the neural network and we are going to go there and have some discussion. Thank you so much. Have a good day.
Bye. Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.